Use unit circle to explain why the graph of the equation y equals sine squared theta minus sine theta will have zeros at x equals pi n and pi over 2 plus 2 pi n, where n is an integer. I guess then really that should say x and x up there to stay consistent. My bad about that. So what do we know? Well, let's pretend like we're trying to find these solutions on 0 to 2 pi. Well, what do we need to do? Let's factor it. So let's say y equals sine of x times sine of x minus 1. Because if we want to find the zeros, then we can say sine of x equals 0 and sine of x minus 1 equals 0. And now we need to think about the solutions here. Sine of x equals 0. Think about that unit circle. When is sine 0? Well, sine is 0 at 0, pi, and 2 pi, if we want to include that. And then sine of x equals negative 1 will give us sine of x equals positive 1. When is that true? Well, that's going to happen straight up at pi over 2. So if you think about that first set of solutions, the 0 and the pi. So from right here, if I go around by a factor of pi, I hit that solution. If I go around another factor of pi, I come back to that solution, and I can keep going around in that manner as many times as I like. That's what this is saying by x equals pi n. If n is 0, I'm at 0. If n is 1, I'm at pi. If n is 2, I'm at 2 pi. If n is 3, I'm at 3 pi. Etc., etc., etc. So I'm just going to continue to revolve around and hit those zeros. Now, compare that then to the other solution, which is pi over 2. Since we're looking specifically for the sign of y, the sign of x equaling 1, that only happens at one spot, pi over 2. So for this, I have to go a full revolution around, which is 2 pi. So that's what pi over 2 plus 2 pi n is saying. If n is 0, I'm just at pi over 2. If n is 1, I'm at pi over 2 with a full revolution. And then any other multiple of n will do the same thing. It's just spinning me around that unit circle.